In this video, we're going to be taking a look at graphing polar equations, that is, equations that are polar in form. Now, we know how to graph Cartesian equations or equations in rectangular form. We have a special grid that we use for that, and we say that if y is defined by some function of x, then you can plug in various x values, and it will spit out various y values. And when you plot those points as a coordinate pair, if you do that for a bunch of points on the graph, then you end up with a picture. Sometimes it's a line, sometimes it's a quadratic, could be any number of things, right? Sometimes it's a sine wave, we've done that. But in this video, we're going to look at graphing equations that are polar in form. I'd like to start with the graph of r equals 6 times the sine of theta. R equals 6 sine theta. And the reason for that is that's exactly what we graphed on the previous screen, but in this case, I want to show you how to graph it using polar points rather than having to convert it first. So I'm going to start by graphing y equals 6 sine theta in polar form. So I'm going to need my polar graph paper to do that. So here's some polar graph paper. And before I begin, I also want to set a scale. Last time I let this mark here be 1. But I know from experience that's not going to be big enough this time. So this time instead I'm going to let every other one of these things be 1. So there's 1, 2, 3, 4, 5, 6, 7, 8. So my graph could be as big as 8 because I'm on a circle. This is also 8, this is also 8, and so on. Okay? Now, in the same way that we usually pick some x's and figure out what y is based on what x is, how y is defined based on x, we're going to do the same thing, but we're going to let theta be our independent variable and r be our dependent variable. Remember that we've been writing equations r in terms of theta. That implies that theta is the thing we're going to plug in and r is the thing it's going to spit out. Now, that's a little confusing because for xy equations, we have an input of x and an output of y. And for some reason, conventionally, we put r first in the set of ordered pairs. We have r first and then theta, and so it looks like r gets plugged in and theta is what gets spit out. But in fact, because of the way we write the equations, it's just the opposite. So I know this is confusing, but that's just the convention that's been used for probably centuries. So let's pick some theta values and see what happens to r as we do that. I'll start by putting my chart up here, and then I'm going to pick values of theta that I know are easy to take the sign of, because I have to do these computations. Every time I pick a theta value, I'm going to plug that number in there, take its sign, and then multiply the result by 6. So let's start with theta equals 0, and then we'll go to pi over 6, pi over 4, pi over 3, and pi over 2. Those are the values that are really easy to take the sign of because we know them, we're familiar with them, or we can look them up on a table. We've all been working with the tables of values now for quite some time. So let's start with our theta equals 0. We're going to plug that value in here and see what happens. That makes this equation r equals 6 times the sine of 0. What is the sine of 0? Well, it's 0. And so that makes this value here 0. And when you multiply 6 by 0, you get 0. So if theta is 0, the sine of theta is 0, and 6 times 0 is also 0. So my output here is r equals 0. All right, now we'll do the same thing for pi over 6. The sine of pi over 6 is a half. So when I plug pi over 6 in here, sine of theta becomes 1/2. Do the arithmetic, 6 times a half, you get 3. So I'll get a 3 there. All right, now I'm going to plug in pi over 4. The sine of pi over 4 is the square root of 2 over 2. When I multiply that by 6, I get 3 times the square root of 2. That's just 6 times the square root of 2 over 2, and I reduced it. The next value in my table is pi over 3, the sine of pi over 3 is the square root of 3 over 2. That gives me this 3 times the square root of 3. And last but not least, at least for now, the sine of pi over 2 is 1. And 6 times 1 is 6. So now these values are going to be easy to plot, but these values are going to be hard to graph because these circle radii are integers, and so in between they're halves and quarters, and in other words, these would be easier to graph if I knew what they were approximately in terms of a decimal. If I stick those into a calculator, for 3 root 2, I get approximately 4.2426. I don't need that much to graph it. 4.2 is quite adequate. My scale here is fairly small and tight, so I'm not going to be able to graph anything more accurately than that. 3 times the square root of 3 is 5.196, so I'm going to call that 5.2. Oops, forgot my decimal point there. 5.2. All right, so let's graph some of these points. Let's graph all of these points. The first point I have is when theta equals 0, r equals 0. So I have a point 0. Let me do it this way. 0 around, so don't move around from the pole, from the x-axis, and don't go out either, no radius. So that's actually just the point, the pole, otherwise known as the origin. That is a point. I'm going to use a different color actually. That is a point on my graph. Let's see, what color should I use? Something that will stand out. Maybe blue. So there's a point on my graph. The next point on my graph is the angle pi over 6 and the radius 3. And as I've said before, I tend to think it's easier to go figure out what the angle is going to be and then go out from the origin or out from the pole 3 units. So let me figure out where my angle is first of all. It's this angle right here. And I'm going to go out from the pole. Notice that these circles or these marks here translate to this is 2. So that would be going out 2. This is going out 3. So I want to point right there. I'm going to erase this line because I don't want it to be in the final graph. So where is that point again? On the line pi over 6, around 3. It's right there. So I've gone out 3 units and around pi over 6. Or I've gone out to this line pi over 6, I've gone around to there, and then I've gone out 3 units on that line. Just by way of a reminder, that's a 1, that's a 2, and this is 3. Okay? All right, what's our next point? Our next point is pi over 4, 4.2. So this time I'm going to be on this line. That's the line 0 radians out to pi over 4 radians. And I need to go out on that line 4.2 units. So let me get my pen. And I'm going to count here 1, 2, 3. There's 4. That would be 5. There's 4.5. So 4.2 is right about there. Now, since this is the first time we've done this, I think it's a good time to stop and take stock of what we've done so far. This was my first point. My second point was here, and my third point was here. If I try to connect the dots, I'm going to get something that looks kind of like this. Notice that I'm going in the order that I plotted those points. I plotted this one first, this one second, so my first connection was from here to here, and then my next connection was from here to the next point that I plotted. And then that's going to continue, but I wanted you to see that that's what I'm doing. So let's see, what have I done so far? I've done this one, and this one. So my next point is pi over 3, 5.2. So now I'm going to be on the line connected to pi over 3, but I need to go out. Let's see, 1, 2, 3, 4, 5. This would be 6. There's 5.5. So 5.2 is about, let me try that again. It's right about there. And then if I connect that to the previous ones, it looks something like that. Now this graph is going to be a little bumpy. For one thing, I'm drawing it by hand. For another thing, I don't always draw the straightest lines or the smoothest curves anymore. But it'll give you an idea of what's happening. And that's really all that's important to hear. So let's take a look at our next point. We've done this one now. Pi over 2, 6. So this time, I'm going to be on this line, and I need to go out 6. So from here, from the origin, from the pole, I'm going to go 1, 2, 3, 4, 5, 6. So that's a whole number, so I know that I just put my point there. And then when I connect these, I'll get that. All right, I've managed to tidy those up just a little bit. It's starting to look more like a smooth shape. And we've just done our last coordinate pair on this list. The thing is, I can't tell what's going to happen next or even what happened before. So it behooves us, I think, to continue. I'm going to run out of room pretty quickly here. So I think what I'm going to do is try to move this. Let's see if I can just do it this way. Not quite. I'm going to have to move my table over and make room for another table, which, as you can see, I have already begun. That's going there. I apologize. I don't know if you remember this from previous videos, but when I move things before I start recording, they don't stick. So if I try to move something over and then hit record, it goes back to the way it was before I moved them. So, and I don't know why it's not working very well. Anyway, that should do us after some space to do the next quadrant, right? And when I say the next quadrant, if we were looking at this, well, actually it applies here too, going from 0 to pi over 2, that's what we've just done here. So now I'm going to go from pi over 2 to pi. Well, I've already got pi over 2. That would normally be my first entry here, but I'm going to the next one that I'm comfortable, familiar with is 2 pi over 3. Remember that if we think in terms of pi over 6's, I have 1 pi over 6, 2 pi over 6, which is pi over 3, 3 pi over 6, which is pi over 2, 4 pi over 6, that's 2 pi over 3. It reduces to 4 pi over 3. So that's my next one. And the reference angle here is pi over 3. So I need to figure out what the sine of pi over 3 is and then check whether it's plus or minus. The sine of pi over 3, I've got that actually here, it's 3 root 3, 5.2. And because I'm in quadrant 2, between pi over 2 and pi, sine is positive. So here I'm just going to get the same value as I did here. So that's going to be 5.2, and it's positive. The next one's 3 pi over 4, so that's this line here. My reference angle is pi over 4, so I'm going to get the same numerical value as I did here, 4.4. And it is also still in quadrant 2, so it's also positive. 5 pi over 6, well, that's this one here. The reference angle is pi over 6. The value is 3, and it's positive. And pi, when I plug pi in for sine, I get the sine of pi, which is 0. One way to remember that is that if you are, use my pointer, if you are around here, then anywhere on this line, if you have a point anywhere on that line, let's just put one here, its coordinates are cosine theta, comma, sine theta. That's for x, comma, y. So that's in a different set of coordinates. But notice that the y value here corresponds to the sine value, and the y value here is 0. So the sine of pi is 0. Let's get rid of those. So the sine of pi is 0, so that's going to go there. And now we can plot these points. I have 2 pi over 3, so I'm on this line, and out 5.2, so let's see. 1, 2, 3, 4, 5.2, so I'm about there. Then 3 pi over 4, so now I'm on this line, and 4.2. So 1, 2, 3, 4, and 4.2 is about there. 5 pi over 6, now I'm on this line. I'm going to go out 3, that's there. And pi, the angle pi, which is this angle here, so I'm on this line, and I'm back at 0. So I need another, I'll do a different color. I'm going to land right there again. And when I connect these dots, I get something like this. And lo and behold, we have a circle, which instead of being centered at the pole, is centered 3 units above the pole. And this is exactly the same circle as we got when we graphed it by first changing the polar equation into Cartesian form first. But as you can see, you can plot points in polar form, so you don't have to convert it. Now, some of you might argue that converting it is less work than graphing it in polar form. But either way, this is a new idea. This idea of polar coordinates and graphing polar equations, these are new ideas. And so however you look at it, you're learning something new here. And whichever approach you ultimately end up taking, that approach is going to be something you haven't done before. So by way of giving you as many tools as possible, we now know how to convert polar equations to rectangular equations, and then we can graph the rectangular equation. Or we also now know how to graph polar equations, just leave them in their form and do our point plotting that way. Now, once you've done a few of these by hand, you don't need to necessarily continue doing them by hand. You can graph these on Desmos. I'm going to do a separate video to show you how to graph polar equations on Desmos. That won't need to be a very long video because it's just a question of notation. But once you've learned how to graph them by hand and why they appear the way they do, then we can just do them on a graphing calculator. Your TI-84 or TI-83 will graph them as well, as long as you're in the right mode. But this is a class on trigonometry, and I want to make sure that you understand where these graphs are coming from, why they turn out the way they do, before you just go to Desmos to graph them. So in that light, I'm going to do another example of graphing a polar equation in polar form. Before we do though, because I'm going to be using the same graph paper, I want to tell you how I knew how big to make my scale. Remember when we graphed this the first time, I said that my radius needed to be half this value? Well, if the radius is half of 6, then the diameter is 6. I also knew from experience that my circle was going to be sitting on the x-axis, if you will, and going above it. So the diameter needed to be 6. And I wanted to be able to count even numbers here. So I counted the total number of divisions I had here, and I had 13, 14, 15, I had 16. 6 doesn't go into 16, but the next number down that it does go into is 12. So that made this number right here, this line right here, 6. That's this one right here. And every other line is 1. So this was 1, 2, 3, 4, 5, 6, and so on. All right, so I'll start with that on the next screen and show you how, I'll give you the equation, then I'll show you how to decide what the scale should be. So we'll start with a clean slate and a new equation, 1 plus 3 cosine theta. R equals 1 plus 3 cosine theta. Now the 3 cosine theta part, we just graphed that before. Yes, we had a 6 here, and yes, we had a sine here, but we know how to graph those. It's this 1 plus part that's new. So the first thing to do, I think, is to set the scale. We know that this number right here, if we didn't have this 1 plus, this number right here would determine the diameter of the circle. So I'm going to need to make sure that the diameter is at least 3. And I also know from experience that this is going to add something to it. So I'm going to make sure that my diameter can be 4. That means my radius needs to be 2. So I could actually come all the way out here and make this 2. But I don't want it to be too big, and I also know something else about the graph, so I'm going to pull it back just a little bit. Let's make this 4. Now, one of the reasons I made this 4 and not this last line here, or the one before it, is that I counted the number of marks, and I think there are 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, or 16, so I'm off a little bit. So I could make this last one 4. But again, I want to pull it in just a little bit. So if that's 16, 15, 14, 13, 12, let's make this mark 4. This one right here. I'm on the wrong axis. So that one right there is going to be 4. If that's 4, and there are 12 units, 12 marks between there and 4, then every third mark is 1. So I have 1, 2, 3, that's 1. 1, 2, 3, that's 2. 3, there's 3. And then 5 would be out here. I don't think I'm going to need to go as far as 5, but at least we have a scale now. Okay, the next step is to make a table of values. Theta is my input, and R is my output. And I have 0, pi over 6, pi over 4, pi over 3, pi over 2. From experience the last time, I also need 2 pi over 3, 3 pi over 4, 5 pi over 6, and pi. And I think that should do us from now. That's r and theta. There's theta is the angle. R I don't know. So let's figure out what the answers to this question are when I know various different values of theta. When theta is 0, plugging a 0 in here, I'm going to get cosine of theta, which is 1, multiply that by 3, I get 3, add 1 to that, I get 4. So in this case, when theta is 0, r is 4. Now I can plot that point. I think I'll stick with blue. It's pretty easy to see, I think. 0, 4 is not 0, 4 somewhere up here on the y-axis. It's 0 radians. So I'm somewhere on the pole, somewhere on the x-axis, and out to a radius of 4. I have a point right here. My next point is pi over 6, or my next theta value is pi over 6. Cosine of pi over 6 is the square root of 3 over 2. But I need to multiply that by 3 and then add 1 to it. So when I come back to this, I'm going to leave that like that for now. That's the exact value. For graphing purposes, we're going to want a decimal. So I'm going to find all of the values in both of these tables now and come back to these and get decimals. I think I'll do maybe a couple more. I'll do pi over 4, and then I'll do a few off screen, and I'll do one of these on screen again, just to remind you. So let's go find the value that goes in the r column if theta is pi over 4. The cosine of pi over 4 is the square root of 2 over 2. 3 times that plus 1. All right, I'll do one more. The cosine of pi over 3 is a half. So I'm going to have a half times 3, which is 3 halves, plus 1. Now, 3 halves plus 2 halves is 5 halves. So another way to write that would be 5 halves, or 5 halves, or 2.5. That's the decimal for that one. One more, because it's actually pretty easy. The cosine of the cosine of pi over 2 is 0. So this is 0. 3 times 0 is 0, and I get just 1. All right, I'll do a couple of these other ones off screen, and then I'll come back and do one more on screen. Okay, here are the first couple of values. Let me show you how I've been finding these. I have 1 plus 3 times the cosine of an angle. And the angle I'm going to plug in this time is 5 pi over 6. That angle is, let's see, it's this one right here. So the angle 5 pi over 6 is this angle right here. It's in quadrant 2. So I know that the result of taking a cosine is going to be negative. So I'm going to have 1 minus 3 times the cosine of the reference angle in that quadrant. And the reference angle to 5 pi over 6 is pi over 6. So I'll put pi over 6 in. And now I need to figure out what is the cosine of pi over 6. Well, that's the square root of 3 over 2. I'll make my 1 into a 2 over 2. And then I have 1 minus, or 2 over 2 minus 3 root 3 over 2. And now I have a common denominator, so I can write that as 2 minus 3 root 2 all over, 3 root 3 all over 2. So that's all I'm doing to find these values. Let's stick that in its place in the table. 2 minus 3 root 3 over 2. And then we'll do pi together, shall we? Get rid of this scratch work. I have 1 I have 1 plus 3 times the cosine of an angle. That angle this time happens to be pi. 1 plus 3 times, what is the cosine of pi? It's a little bit harder to remember, but if that's pi, and this is a radius of 1, then that point there has coordinates -1, 0. And since coordinate points in the xy system are cosine, sine, the angle is the cosine of the angle is -1. So my answer there is when theta is pi, the cosine of theta is -1. So that evaluates -1. So I have 1 minus 3, which is -2. So that's what goes here. Now the next thing to do would be to plot these points, except that some of them are going to be kind of tricky to plot since I don't really know their values in a way that I can use them on the graph. So I'm going to take a moment and just go off screen again on my calculator, and I will come up with some decimal approximations for, I don't need one for this. This is 5/2, which I know to be 2.5, so I'll just call that 2.5. But there are 4 values here whose decimal approximations I don't know. So I'm going to go off screen and figure that out. I know you know how to use a calculator, so I'm not worried that you'll have any trouble figuring this part out. All right, let's find these values. Let's look at these pairs of points. I have 0, 4. That means I'm going to go out around 0. So I'm going to stay on the line that represents theta equals 0. And I'm going to go out 4. So that means I have a point right here. I've already plotted that one. The next point in my chart is pi over 6, comma, this is that 3 root 3 over 2 plus 1, that about 3.6. So I want to be at the angle pi over 6, so on this line here, and out from the origin by 3.6. So somewhere in here. Well, this is my circle with radius 2, so that would be the point pi over 6, comma 2. Here's the one with radius 3, so this is the point pi over 6, comma 3. And here's the one with radius 4. Pi over 6, comma 4 would be right there. So I need to be somewhere between 3 and 4. In fact, I'm at 3.6, which is just a little more than 3.5, so I'm going to put my point right about there. My next point is pi over 4, about 3.1. So that's going to put me somewhere along this line, somewhere just beyond the circle with radius 3. So that's going to put me about there. The next point is pi over 3, 2.5. I'm going to give you just a few seconds to see if you can figure out where on the graph I'm going to plot this point. The angle is pi over 3, so find that line. Then somewhere along that line, 2.5 units out from the origin, that's where the point is going to go. Have you found it? Right here. The next one is pi over 2, comma 1. Can you find that one? Find the pi over 2 line. It's actually an angle. The line just represents how far around the circle you've traveled. Now from that angle, on that line, go out from the origin, go out from the pole 1 unit. Your point should be right here. All right, let's connect these dots and see what we've got so far. I started here. This was the first point that I plotted. The second one I plotted was this one. So that's why I've connected them in that order. It kind of looks like I'm just going to get a circle, right? So maybe at this point I should cheat and just draw in the rest of my circle like this. The thing is, it's not a circle. So we actually need to keep going. The next point on our chart, it's the second column here, it's this new quadrant we're working in, is 2 pi over 3 negative 1/2. So let's find 2 pi over 3. It's there. And that's this line here. I could go all the way along here and come out the other side. The reason I'm doing that is that I actually need to go to that line, 2 pi over 3, and then instead of going from here out in the direction of the arrow that I just placed, I need to go backwards. And I need to go backwards 1/2 of a unit. So that's going to put my point right about there. That's not quite right. Let me see if I can fix that. That's better. Now I'm going to erase the line. And let's go over again just how I got that point. I went around to the angle 2 pi over 3, and then I went backwards 1/2. So I went around to the line 2 pi over 3. That's this line right here. I want my point to be on that line. And then instead of coming to the pole or the origin and going 1/2 in this direction, I went 1/2 in this direction. I think I've ended up putting my point on. Oh, no, it is on the right line. Okay. This is the line for 2 pi over 3. And if I go backwards, I end up on this part of that line right there. So there's the point back 1/2. And that's what we mean by having a negative radius. So if I connect that point now to the rest of them, I get something that looks like this. And then I can keep plotting. My next point is 3 pi over 4, negative 1.1. So I'm going to go around to 3 pi over 4, and then from the origin, instead of going 1.1 in this direction, I'm going to go 1.1 in this direction. So there's my 1, so my point's going to go right about there. There it is. The next one is 5 pi over 6, negative 1.6. So I want this line, and that equates to this line if I end up going backwards, and I want to be at 1.6. And 1.6 is going to be about, that's 1, that's 2, 1.6 is going to be about there. And the last point on the chart so far is pi comma negative 2. So I'm going to be on the line associated with the angle pi. This is the angle pi, so that line right there. And I want to go negative 2. So instead of going to this line and then coming out in that direction from the origin, I'm going to go backwards. So I end up with a point right here. I'll connect these points, and it kind of looks like I might be doing a spiral, right? So maybe I just cheat and do something like that. But it's not a spiral either, so we need to keep going. The last one of these we got through pi, and we were able to stop because once we started graphing, we ended up back where we were. We knew that the graph was complete. In this case, though, we got all the way to pi radians, and we found a point associated with theta equals pi, but it didn't complete the graph. So we need to graph more of our angles, right? So this is quadrant 1, this is quadrant 2. We need to graph quadrants 3 and 4 as well. Here are a couple of tables. This will be my angles for quadrant 3. I got these angles by just looking at the values on the circle that I was given here. I can memorize these, or I can figure out that if this is 6 pi over 6, this must be 7 pi over 6. But since they're labeled right on the graph, I don't see any reason why not to just grab them from there. So I used the reference angles of pi over 6, pi over 4, pi over 3, and pi over 2. Those are reference angles of pi over 6, pi over 4, pi over 3, and pi over 2. So that's how I picked those. I didn't do this 13 pi over 12 or this 17 pi over 12 because I don't know the values for those. I can stick them in my calculator and I could get a little bit more accuracy with my graph if I did that, but it's not really necessary. So that's where I've got these values from. And then in quadrant 4, I'm using these 4 values. Again, my reference angles are pi over 3, pi over 4, pi over 6, and 0. So pi over 3, that's my reference angle, pi over 4, pi over 6, and 0, which is the same as 2 pi in terms of radians, or at least it's coterminal. My next job is to figure out what goes in the R column. So I'm going to do that off screen, except for maybe 1 or 2. Actually, in the end, I decided just to do them all because I'd rather spend the time focusing on why I got the values that I did. So I'm going to grab one. Let's use this one here. 5 pi over 4 is this angle right here. 5 pi over 4 has a reference angle of pi over 4. I was therefore looking for the cosine of pi over 4, but since I'm in quadrant 3, that value is going to be negative. So the cosine will be negative, then I'll have whatever that is times 3. So this becomes 1 minus 3 times that negative cosine, or 1 minus 3 times that cosine value. So that's why that ended up being negative 1.1. In the end, if you notice that this reference angle of 5 pi over 4 is the same as this reference angle of 5 pi over 4, because in both cases, the cosine of pi over 4 is the square root of 2 over 2, but it's negative. In quadrants 1 and 4, my reference angle of pi over 4 is positive. So I get 2 plus 3 times the square root of 2 over 2. Anyway, so that's how I found those values. I basically just copied them from here. Not quite. There was one difference here and one difference here. But basically I could copy them from here, copy these ones from these ones by recognizing that the values were going to be the same depending on the sign or depending on the quadrant that I was in. These two were going to be the same because quadrants 2 and 3 are negative for cosine, and these two would be the same because quadrants 1 and 4 are positive for cosine. So that's how I got those values. So now let's go ahead and plot these. I'm going to plot 7 pi over 6, negative 1.6, 5 pi over 4, negative 1.1, 4 pi over 3, negative a half, and 3 pi over 2, negative 1. 7 pi over 6, negative 1.6 is back here. Which line is this? It's back here somewhere. And at 1.6, let's see, I want to be negative 1.6. I want to be 1.6 in that direction, so it's going to be about there. Pretty good. The next one is 5 pi over 4, negative 1.1. So I'm going to be along this line, which, because I'm going to use a negative value, goes back here. Negative 1.1 is right about there. Next, I'm going to plot 4 pi over 3, negative a half. So I'm going along this line, and then I'm going to go back out to negative a half, which is about, oh goodness, 1, 2, it's about there. I started to graph this next point, and I realized I'd made an error. 3 pi over 2 is my reference angle. Sorry, pi over 2 is my reference angle. So if I stick pi over 2 in there, I get the cosine of pi over 2, which is 0. 0 times 3 is 0. When I add 1 to that, I get 1. So this one should actually be positive 1. So now I'm ready to plot the point 3 pi over 2, comma 1. And that is here. So let's connect the dots from where we left off the last time to where we've landed. We get something that looks like this. Now clearly we're still not back to where we started, so we need to keep going. I'll do quadrant 4 next. 5 pi over 3 is here. And I want positive 2.5. So along this line, out to 2, there's 2, there's 3, so 2.5 is about there. Then 7 pi over 4, comma 3.1, so I'm going to go to 7 pi over 4, and then out to 3, and then just a little bit more than 3. 3.1 is there. The next one is 11 pi over 6, and then 3.6, so I have 3 here, and 4 here, so 3.6 is going to be about there. And my last point is 2 pi, comma 4, so I'm on this line here, and my point is right there, which is where I started. Now, that's really good news, because that means I've come all the way around, and I've ended up where I started, so that means I know that the graph is complete. I could go around again, but I would just get another cycle of the same graph. I would start sketching over the graph I've already got. So that's how I know that I'm done, and I can go in and connect these dots. Now, when I did that just now, it helped me find an error. This side of my graph just looks kind of too small over here. Look, see how much width there is to my graph here. It just looks kind of squished on this side. And I think it's this point here. So I went back and looked at what those 2 points were. On this side, my reference angle is pi over 3, and I'm at 2.5. On this side, my reference angle is pi over 3, and I'm at 2.25 or 2.3. So this point is in the wrong place. I'm going to move it to where it should be, which is here. And then I'm going to erase, I'll do this off screen. I'm going to erase these 2 lines, and I'm going to reconnect them. That's much better. All right, this video is already almost 40 minutes long, so I'm not going to go too much longer on this one, but I would like to point out something I think is really interesting. This equation, this is the thing we've just graphed, r equals 1 plus 3 cosine theta, has some hints in it. I can tell you exactly, let's see, I've got to find a highlighter that's going to work for me here. I think I can use the blue one. I can tell you exactly how big this loop is going to be and how big this loop is going to be by looking at this equation. Notice first of all that there's a plus in the original, and then notice that if I add the 1 and the 3, I get 4, and that's how wide my big graph is, right? That the outer sort of loop, if you will, has a diameter of 4. Also notice that if I subtract those, at least in terms of their absolute value, I get 2. And that's the size of my inner loop. Now, I think that's particularly fascinating. We're going to be playing around with some more of these, and I'm going to change these two values here so that they're 1 and 5, 2 and 6, maybe 3 and 3, so they're the same, and we can look at those. And I would invite you, as we do that, to predict what the graph is going to look like based on these two values. This is actually something that wants to be a circle of radius 1.5, but this plus 1 is throwing it off. Now, it's not throwing it off for the same reasons as it would in rectangular coordinates. If we had graphed y equals 1 plus 3 cosine x, then we'd get a cosine graph with an amplitude of 3 that was shifted up 1 unit. In polar coordinates, it's something else that's happening. And we can talk about the comparison of those two graphs, the rectangular version and the polar version, but I want to do that on a separate video for a couple of different reasons, not least of which this one's already almost too long. In the next screen, I'm going to do one more example of this type of graphing a polar equation, but I'm going to do it a lot faster because I want you to see another example, but I don't want to have to spend the time. I don't want you to have to sit through the tedium of seeing this part again. So let's do one more example of graphing a polar equation. In the previous example, the number in this position was smaller than the number in this position. This time that's reversed. So I'm going to make the argument that I can tell something about this, the graph this thing is going to produce by the sum of these two numbers being 10 and the difference being 2. The other thing I want to point out is that the previous one was a cosine and this one's a sine. Remember that x equals r cosine theta and y equals r sine theta. So if you have an equation, a polar equation that has a sine in it, it's kind of a y-like thing. It's a y-related thing. An x, if there's a cosine here, then it's an x-related thing. And by that, what I mean is that when we graphed the cosine, the graph we did a minute ago, which was 1 plus 3 cosine theta, we ended up with something that was kind of not like that. It wasn't that shape, but it was kind of around the x-axis. Right? It was a cosine thing, and it kind of hugged the x-axis. When we graph a sine kind of thing, it's going to hug the y-axis. So it'll try to do this. It might do this, or it might do this, but it's going to do it kind of around the y-axis. This graph is a sine, so I expect it to sort of focus up here rather than off to the side. The other thing that I'm expecting is that the diameter of this thing could be as big as 10, because the sum of the 6 and the 4 is 10. The difference is 2, and that'll come into play as well. But basically, I need to make sure that I have enough room to graph out to 10. So what I'm going to do, remember that the graph paper that I'm using goes out to 16. So let me count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm going to have to use increments of 1 instead of increments of 2 because there's not enough room here to double them up. I can't get out to 20 marks, so I can't use a range of 2 of these for 1. So this is going to have to be my 10. That's enough information for me to get ready to graph. And now what I need to do is go find the values that go in this chart. Now I know you'll be able to do this part even if you just use your calculator. So I'm not going to bore you with this part. I'm going to go find these values and then I'll come back. Okay, so here we have our tables of values, and I'm just going to start with 0, 6, pi over 6, 8, and so on. So 0, 6 is a theta of 0, so I'm starting here and not rotating at all, but I'm going to go out 6 units. So my first point is here. My next point is on pi over 6, and I'm going to go out 8, so that's the circle that has a radius of 5, 6, 7, 8, so my next point is here. Then we have pi over 4 and 8.8, that was 8, so I'll go out not quite to the next one, next line. The next line would be 9, I don't want to go that far, 8.8. Then the next one is pi over 3, 9.5, that's 9, so 9.5 is about there. Then we have pi over 2 and 10, and that is right here. And I'll just double check. Follow along this circle. I end up at, this is the circle with radius of 10, and I'm at 10 at the angle pi over 2. So that's the first quadrant. And I'm just going to keep going. The second quadrant, the first point is at 2 pi over 3, and I want 9.5. Remembering that this was 10, 9.5 is there. Then 3 pi over 4 with 8.8. That was 9.5, so that's 9, so 8.8 is there. Now we want 5.6 and 8, so that's going to be about there. And the last one in quadrant 2, it's not actually in quadrant 2, it's on the boundary between quadrants, but that is 6, 1, 2, 3, 4, 5, 6, radius of 6 at the angle pi. What do you think? Is it going to be a circle? Should I just assume it's going to be a circle? Let's keep going and find out. My first point in quadrant 3 is 7 pi over 6, comma 4. Let's see, that's there. Then I want 5 pi over 4, 3.2. That's about, well, let's see, that's about there. Next, we have 4 pi over 3 and 2.5. That line there at 1 to 2.5 is there. And 3 pi over 2 and 2. That is there. Well, it's definitely not a circle. Maybe it's going to be a spiral. Could be a spiral. Let's keep going. 5 pi over 3, I'm in quadrant 4 now. 5 pi over 3 is at 2.5. That is there, I think. Let me just double check that one. 1, 2.5, yeah, that's a little bit out. Let me try that one again. There we go, that looks a little bit better. All right, the next one is 7 pi over 4 and 3.2, so that is there. We're almost there. Now we have 11 pi over 6 with 4, that is here. And then finally we have 2 pi, which is at 6, and that is actually already there. So that also helps me know that my graph is complete. I've come, I would say full circle, but that would be a misnomer. I've come all the way around to where I started. So that's one of the ways I know that my graph is complete. Now I started here. I started at 0, 6, and I ended at 2 pi 6. That was the first point that I plotted. The next one that I plotted was this one, and so on around. So I'm going to start drawing here, and I try to connect the dots. I get something that looks like this. It's actually quite difficult to do, but I'm getting there. All right. That is the graph of r equals 6 plus 4 sine theta. There are a couple of things to notice here. One is that it's more sort of y-oriented than x-oriented. It's not kind of hugging the x-axis, it's hugging the y-axis. And that's because it's a sine. Remember we said that since x equals r cosine theta and y equals r sine theta, this is a sine graph, so y equals r. That's just a mnemonic. There may be more of a relationship there than I'm giving it credit for, but for me, it's just a way of remembering that a graph that's a sine graph, because y equals r sine theta, is going to be more y-axis oriented. So that's one thing to notice. The other is that the sum of 6 and 4 is 10, and look what the radius of, look at the most extreme value of this thing. The radius of this, if you count from the pole, this thing goes out 10 units in that direction. The difference between 6 and 4 is 2. I'll use a different color for this one. And if you count out here, you get 2. So it's 10. The sum of these gives you the sort of the radius in one direction. Radius is a bit of a misnomer, but we'll go with it for now. 10 is the radius in one direction. 2, the difference of these two numbers, is the radius in the other direction. On the previous graph, we had a loop, and we had the sum of the two numbers. We had a 1 here and a 3 here, and the radius, the most extreme value, was in this direction as well. But bear with me. The most extreme value, the sum of the two values was 4, and the radius, the large radius, was 4. The difference was 2, and the loop had a size of 2. The difference between that one and this one is that in that case, the 1 was smaller than the 3. In this case, the 6 is larger than the 4. That's why we don't have a loop, but we have like a missed loop almost. It looks like it wanted to be a loop there, but it didn't make it. It wasn't strong enough. So because this 6 is bigger than the 4 sine theta would have just been a circle, and the 6 is adding to that, but it's adding too much for it to give it a loop, right? It's too strong, and it's just pulling it back. So that's how I see these. I am going to graph one more, but I'm not going to graph every single point like I did this time. So I'm going to erase this screen or go to the next slide, and when I come back, we will have another graph to look at and talk about very briefly. Okay, here are the points for my graph. Here's what the first half looks like, and there's the second half. Now, the big things to notice are that since it's a cosine graph, it's hugging the x-axis. X equals r cosine theta. The other thing is the sum and difference of these two numbers here. The sum, 4 plus 4 is 8, so my widest point from the origin, my widest point, or my longest distance from the origin, is 8, the sum there, but the difference is 0. And so I have neither a loop nor a missed loop, right? I don't have just a slight indent the way I did with the previous graph. I have a loop of size 0 or an indent of size 0, the difference between these two graphs. So I think it's interesting that we can tell these things just from the equation. Although graphing them is interesting and fun, we don't always need to do it by hand, but we can get a sense of what a graph of something like this is going to look like just by looking at the equation. This class of graphs that we've been working with is called Limaçons. This is a French accent character called a cedilla. It makes this C a soft C. I'm not going to ask you, I'm not going to quiz you on the pronunciation, but I just want you to know. I've heard this word pronounced Limaçon, Limaçon, but the I in French would be an E sound, and the cedilla here tells me that's a soft C. So I would pronounce that Limaçon. Now, all three of the graphs that we've done so far are Limaçons, but this one is special because this one is one of the ones with a difference of 0 here, so it has neither a loop nor a missed loop. And this one is called a cardioid because if you turn it on its side, it looks something like a heart. Cardioid, cardiac. Okay, so this is called a cardioid, but it's one of a class of graphs called a Limaçon. There are other ways we can write equations like this. Not like this, but other types of equations. For example, I could try to graph r equals the cosine of 4 theta. And we haven't talked about those yet. But this is a good place to take a break, to draw a line under it, as it were. We do need to talk about graphs whose equations look like this, but I'll do that in a separate video. For now, the thing I want you to take away from this video is that this is how we graph polar equations. You will not have to do these by hand for the rest of your life. I may ask you to do one by hand on an exam, for example, but mostly because I want you to get some practice. To prepare for an exam, you'd have to practice graphing polar equations, and that practice will help you observe and recognize patterns in the future. All right, in the next video, we're going to talk about graphing roses.